Our first presenter this morning is Jeff Carlson, and his presentation will be on basics of steel bridge corrosion protection and recent advances in thermal spray coatings. Jeff is the West Regional Director of the National Steel Bridge Alliance. He represents the steel bridge fabricating industry on matters of steel bridge fabrication and construction. Prior to joining NSBA, he spent 7 years as a consulting engineer. He has an undergraduate degree in civil engineering from Colorado State, a graduate degree in structural engineering from the University of Texas, Austin, and an MBA from the University of Denver. Jeff?
All right, give me a sec here to get the right presentation up. Okay, I got it. Yeah. All right, the PDH code for this session is 42172. Again, that's 42172. All right, so thanks, Gary. So as Gary said, my name is Jeff Carlson. I'm the West Regional Director for the National Steel Bridge Alliance. Our session today is steel bridge corrosion protection and recent advances in thermal spray coatings. We get the great pleasure of going at 8 o'clock in the morning after the conference dinner. So as you can see, our attendance is a little bit light, but I imagine people will filter in somewhat after their hangovers cure up a little bit. So our presentation or this discussion today is going to be just an overview of steel corrosion protection measures, and then we'll get in a little bit more into metalizing, which is a newer, it's not a newer coating system, but it's newer to the bridge industry. We're going to delve a little bit into thermal spray coatings, but just a general overview of the 4 basic types of corrosion protection for steel, and then again we'll go in a little bit deeper on a recent specification that's being adopted and going through the balloting process as we speak. So when it comes to corrosion protection for steel bridges, it's really all about the zinc. It's just a matter of how are we going to get the zinc onto the steel. With the exception of weathering steel, that's true. All other 3 coating systems is just it's different mechanisms for getting zinc onto the steel itself. So before we get into that, we want to talk a little bit about the environment's corrosion. This is a little bit of a review for everybody. It's pretty much common sense, but let's just review here. So the most severe would be a marine atmosphere and marine environment, near the oceans, near industrial areas, where the salt spray is great onto the steel itself. That would probably be that is the most harsh environment. Next would be moderate, so some exposure to salts, so maybe de-icing salts in some northern regions where there is water present, but not necessarily a lot of salt and a lot of chloride, and maybe some exposure to industrial areas and some pollution, but not necessarily as bad as severe. And then finally, mild or rural. This is a picture just for you, Ronnie. This is a picture of El Paso. This is what we would consider to be mild. Somewhere where it's arid, they're not de-icing salts used, we're not in the north, and it's just more of an arid environment, and it's just not exposed to moisture and pollution as much as the other 2. But before we get into this, I want to make a plug for a document that I'm going to talk a little bit about later. This is a table taken from the Federal Highway document. It's part of the Steel Bridge Design Handbook, but it gives rates of corrosion, general rates of corrosion for different environments. So there's rural, there's urban, there's semi-rural, there's industrial and marine. As you can see, the best case scenario for corrosion loss and carbon steel loss would be in Phoenix, Arizona, 0.26 mils per year. And then the worst, down here at the bottom, would be Curie Beach, North Carolina at 28. This is where the Federal Highways conducted a lot of their testing for a lot of their coating systems and various corrosion protection systems for bridges. It was down in Curie Beach, roughly 80 feet from the coast. So that's probably the worst environment. So we go from Phoenix to the coast, so we capture all the 3 environments that we discussed earlier. And I'll talk a little bit about this document in a little bit. So I think all of us know about the main corrosion protection systems for steel bridges, but there's maybe one that we haven't heard of. First one being paint. Everybody knows about paint. But there has been some recent advances in paint and some recent systems that maybe we're not all aware of. And perhaps some of us are still stuck back in the 70s and 60s and think that that's what all paint systems are. And we're here to tell you that that's not true. Paint systems are very good, and when done properly, can last a very long time. Weathering steel. Weathering steel's been around a long, long time, and again, when done properly and when in the proper environment, weathering steel can perform very good just as long as paint. Galvanizing, I think most of us know about galvanizing. It's more common in the building industry, but it is making some comebacks in the bridge world. And in the right circumstances, it can be a very good system as well. And last but not least is metalizing. How many people don't know what metalizing is? Everybody knows what metalizing is. Okay, only a couple of us. All right, so we'll talk about metalizing and some recent specifications that have come out for metalizing. There have been some bridges built in the US using a metallized system, also called thermal spray coating. This is a bridge, I believe, in New Hampshire that was metallized up in that area, and there are a handful of fabricators now that do metalizing in-house. So first let's talk about paint and its history. So pre-1970, over here, we really didn't recognize the benefits of surface preparation, cleanliness, surface profile, stuff like that, and that's really where some of the bad paint perceptions come from. There's been a lot of bridges pre-1970 where the paint systems have performed poorly, and unfortunately, that's influenced our perception of paint. But since then, in the 70s, we started to realize the benefits and understand how surface profile and surface cleanliness and surface preparation played a role into good paint systems. Then in the 80s, we started to recognize the benefits of zinc-rich primer, and roughly 80% of owners in the 90s were specifying zinc-rich primer. Then in the 90s and 2000s, we started to recognize the trend at that time was to apply primer in the shop and then do the mid and the top coat in the field. And currently, we're starting to realize that the environment, when we install these, it can play a role in the longevity and the durability of the coating system. So one recommendation that we have is to try to apply all three coats in the shop itself. We just have better control of the environment, better control of the equipment, so on and so forth. Now, the downside to that, or the con of that, would be that we could potentially have issues with handling, damage during handling, so we have to figure out how to touch those up in the field and so on and so forth. But generally speaking, a recommendation that we would have is to try to install them all in the shop, and we just get a better coating system that way. So what paint system do we want to specify? As we can see from this picture, there are definitely paint systems that are good and definitely some that are bad. Clearly some in here don't perform well. This is a test specimens, or a series of test specimens that the Federal Highway was testing, I believe at Curie Beach is where this is from. And as you can see, some do well and some do poorly. So clearly there are some that we would want to specify in a harsh environment and some that we wouldn't. So the conventional paint system would be our three-coat paint system that's been around for a relatively long amount of time. We can either do, it consists of three coats, the top or the bottom coat being a zinc-rich primer, inorganic or organic. Notice that I've highlighted organic, and that's our general recommendation, and I'll touch on that again later. The epoxy middle coat, it's mainly a moisture barrier, but it doesn't perform very well for UV exposure. So it can color and it can discolor. So therefore we use a polyurethane top coat, and that generally acts as our UV protectant, and it retains the color and the gloss longer. Now here's some additional paint considerations. So the zinc protects the steel, and the mid and the top coat protect the zinc. Again, it's all about the zinc, so that's what we want to protect. We have a general recommendation to use the paint system from one supplier. So don't buy your zinc-rich primer from one supplier and your mid and your top coat from another one. You generally may run into problems with that. So that's something we would try to avoid. NETPEP is an AASHTO organization. It's an AASHTO set of documents, the National Transportation Program for Evaluating Products. It's made by the owners and it's maintained by AASHTO and by the owners. So they have some good guidance on just paint selection in general. So we definitely recommend to all the owners in the room and anybody looking to specify the paint system to go to NETPEP. And then finally, the throughput of the fabricator. I mentioned organic is superior, and I highlighted it up here. Generally, fabricators would prefer organic zinc-rich primer to inorganic zinc-rich primer. And that has to do with the environment and the curing rates for organic versus inorganic. An inorganic primer depends on the atmosphere and the moisture content in the air for it to cure. And in some cases can take 24 hours. I believe there's even some states that require it to cure for 3 months. So it really can cause a problem for throughput, whereas organic, that can cure in a matter of hours. So it's definitely advantageous for throughput, and it definitely helps your cost and schedule and efficiency from that perspective. So this is our traditional three-coat paint system. Zinc-rich primer, epoxy intermediate coat, and polyurethane top coat. There are some new paint systems that exist. This one happens to be a polyaspartic 2-coat. I know that this is being used somewhat in the Northeast, maybe not as much in the West, but the same zinc-rich primer, but then we have a polyaspartic urethane top coat. So obviously we have 2 coats instead of 3, so that's going to save us some time and some money. But there are some other advantages in terms of performance from what we understand, but I think a disadvantage to this, from what I understand as well, is that this is only produced from one supplier. There are some other two-coat systems that I'll touch on the next slide, or maybe 2 slides from now, that are produced by both paint suppliers. But the main advantage of the polyaspartic is the time and the waiting time. So as you can see from the 3-coat system on the left, this is wait time, by the way, not how long it takes you to coat it. It's how long you have to wait between coats before you can go to the next one. And these are just general rules of thumb. I think there's some differences within each paint system, but this is just generally speaking. So 30 minutes to recoat after the primer is installed, 4 hours to recoat after the epoxy, and 6 hours for the top coat. Whereas the polyaspartic, the same 30-minute wait time for the zinc, but after the top coat after the polyaspartic top coat is installed or is applied, you can handle it after an hour. So significant reduction in wait time here for a polyaspartic. Now the last thing about paint is other 2-coat paint systems. The polysiloxane top coat. This is one that also exists, and I believe this is used on the West Coast. This is a system that's currently being applied to the Gerald Desmond Bridge in Long Beach, California. But it has similar pros and cons of the organic zinc-rich primer versus the inorganic. It relies on the environment to cure. So similar to the inorganic, it again relied on the environment and the moisture content and humidity in the air to cure. The polysiloxane has similar cons to it. So you can still use it. It's a 2-coat system, which is good, but you still have to wait a little bit longer for the top coats to cure properly before you can handle it, and so on and so forth. So it's being used, and it's a 2-coat system. However, it still has some cautions, and you need to be careful about some things. This is a document that was published by the AASHTO NSBA collaboration a few years ago. It's S8.1. Down here, it is the guide specification for application of coating systems to zinc-rich primers to steel bridges. So it's specific to zinc-rich primers to steel bridges. This was published by and put together by a group of owners, consultants, fabricators, and to give guidance on the application of zinc-rich primers. So our collaboration group, and I'm actually working on a specification for metalizing as we speak, and I'm going to touch on that at the end of the program. But it was the same committee that was working on this spec that is going to be working on the metallized spec. And again, I'm going to touch on that in a little bit. So next, weathering steel. I think everybody knows about weathering steel. It's been around a long time. It has very good advantages, and when used properly and when detailed properly, can perform just as long as paint. Weathering steel is our general recommendation at the NSBA for what corrosion system to use, mainly due to its cost effectiveness. There are some cautions, however, and there are some common concerns regarding weathering steel. First one being staining of piers and abutments. Nobody likes to have the weathering steel bleed and run down the piers and abutments. That is an issue and it can happen, but there are ways to mitigate that. Also, initiating the patina and inconsistent development of that patina is something to have concern about. Mainly this is an issue in arid environments, Arizona, Southern California, West Texas, for example. Some people complain about the fact that it just doesn't form that patina uniformly and at the same time. So it takes several wet and dry cycles to form that patina. So the issue is in a very dry environment, it can form not uniformly, and that can be aesthetically unpleasing. But there are, again, ways to get around that. This is some spec language directly from the Iowa Department of Transportation. It violates the rule of having too many words on your slide, but I don't intend you to read it. The point of this is it's taken directly from a DOT, the Iowa DOT, and it gives guidance for what they do to handle some of this staining and also some of the patina to form uniformly. So the first one there just talks a little bit about the cleanliness and the surface prep for SP6. But the second one there talks about the application of to put the weathering steel through 3 wet and dry cycles before it even leaves the fabrication yard. Now this is something that's not meant to be done in the paint booth and to mess up your throughput. It's meant to be done out in the yard with your summer intern with a hose, where they just go out there and make sure it goes through 3 wet and dry cycles. And that starts the patina before it actually gets into the project location. So it does two things. It allows the weathering steel to start this patina so it forms uniformly, and it also starts the bleeding process, so most of the bleeding occurs in the yard before it actually gets onto the piers. So a very simple thing that you can do, but it can help out very immensely. Now, it's not going to solve your staining problem, but it's going to greatly reduce it and greatly mitigate it. Some other things we can do are use plastic, to wrap the piers in plastic, which I understand is often done during construction, is to wrap those piers for curing reasons and other, just for overall protection. But that's something that can be done as well during construction, because the majority of your bleeding is going to happen in the first couple of months. So if we wrap our plastic during, or wrap the piers during construction, that's something that can just help out and protect the piers. And when done properly, we see that we don't have any staining under this weathering steel bridge. Now, this is also something that can happen. This can also happen at the bottom flange of our girder. It gets dirt and debris and stuff caught on the top of the bottom flange. And this is something that some DOTs, so what do we do when this happens to our cars, right? We clean it off. So some states do the same thing. They clean their weathering steel bridges every few years. So this removes all that debris from the tops of those bottom flanges. And that's where our weak points are, is when you get debris there, water collects and it won't dry out and go through those cycles, which is what it needs. So this is something that some states do. I know for a fact that Iowa DOT does this. It's a low-cost maintenance thing. You don't have to go and repaint. You don't have to mask it. You don't have to go and control all the painting systems and surface prep. You just go out and spray it off with a power washer. So it can be done overnight with low-skill labor. All right, so next we'll move into galvanizing. So galvanizing can be cost competitive if the right circumstances exist. Two things to consider. One of them is inspection of the steel after it is dipped in the tank, and the proximity of that to your fabrication yard and when you're going to require that inspection to occur. So imagine if the steel gets fabricated in a fabricator, it then has to go to the galvanizing tank and get dipped, and then it has to be handled and put on a truck to go back to the fabricator to get inspected. That just adds cost. So that's what we want to try to avoid. So our recommendation would be to allow that inspection to occur in the galvanizer's yard, and then that reduce some costs. Next thing is the location of the galvanizer's tank to the project site. So if it can go from the fabricator to the galvanizer and it's not at least out of the way too much to the project site, that can help our cost out as well. But if you have to go if you have a project in California, it's fabricated in Salt Lake City, and it has to go to Kansas City to get dipped and then back to California, you can imagine the cost is going to be astronomical for that. Other things to consider are double dipping. This is especially an issue for longer bridge girders. It's typically not a problem for the structural and the commercial world because their size of their pieces are much smaller. But for larger bridge girders, if you have to double dip, that's going to significantly add to your cost as well. So if that happens, we may want to think about some other measures. But there's definitely, for wide flange girders, for example, for shorter bridges, galvanizing is definitely a very good option for you, and you should definitely consider it for that. But just don't say do it for everything. There's a time and a place, and we just want to think about which system we specify. One caution, especially for larger, flimsier plate girders, when I say flimsy, I say that tongue-in-cheek. It's more like if we have a thin web with some large flanges and it's just not very stable, and if we dip that, you have the possibility for distortion, and that causes problems for everybody. The owner, the steel fabricator, it looks bad for everybody, so those are some cautions. The AGA does have some documentation, I believe it's on their website now, that gives guidance for how to avoid that. Width to thickness ratios, so on and so forth. So definitely pay attention to the AGA's website. They want to try to help you as well. And last but not least is thermal spray metalizing, thermal spray coating or metalizing. So again, what is metalizing? It's essentially a layer of zinc and aluminum sprayed directly onto the steel surface. Sometimes you use a clear coat and sometimes you don't. There's debate and owner preference on whether or not you need a clear coat or not, and we'll talk about that in a minute. But I generally describe it as a combination of welding and spray painting. It's one way you can think about it. Imagine we have a wire-fed welder, but we have two wires coming together now, and then there's an electric current passed between them, so that melts the material, and then we have compressed air that blows it onto the surface of the steel. One positive of this is the steel can be cold. It doesn't need to be preheated. It doesn't need to go in the galvanizing tank to be possibility for distortion, so there's some advantages to it. But the one main thing that has to be done for thermal spray coating, and one very key ingredient, is the surface prep. The surface profile needs to be angular, and we're going to talk about some of our specification stuff that we put in to address that. But the cleanliness and the surface profile are very important for thermal spray coating. And I'm going to touch on thermal spray again in a second. So let's just kind of summarize the main 4 systems here. So this is just some relative lifespan information. I don't have actual numbers, which I know every owner always wants. But the fact is we just don't have a lot of fantastic data for that. There is some data out there, and the Federal Highway has some guidance on lifespans, but there hasn't been recent advances or recent testing done for lifespan. But generally speaking, I would put galvanizing and metallizing in terms of lifespan into the longest lifespan. And then 2A and 2B, I would say, would be weathering steel and coatings or painting. But again, if detailed properly and if applied properly in the right environment, there's no reason that weathering steel on a paint system can't last just as long as a metallizing and galvanized bridge. So don't be scared off by paint and weathering steel. If done right, it can last very long. Now, relative cost. So I would put galvanizing and metallizing into a higher cost, and Ronnie's going to discuss this, I believe, more in detail later, so I don't want to step on his toes. Next, I would say painting systems would be our next most expensive, and then last would be weathering steel. Weathering steel generally cost, I believe, is 2 to 3%, and again, Ronnie's going to touch on this, more than just typical grade 50. For 50W, it's roughly 2 to 3%, or 2 to 3 cents, generally speaking, more. Oops, too far. This is the Steel Bridge Design Handbook that I referenced earlier, that table, that gave corrosion rates. This is where that came from. This document is roughly 33 to 35 pages long, and it discusses all the pros and cons of each corrosion protection system. The date down there, which you can't read, says 2012, but there's a new one that just was updated in 2015, and it's currently available. You can get this document from our website, steelbridges.org, and you can also get it directly from the Federal Highways website. So a very good reference document when you're trying to decide which corrosion protection system to use. All right, last is our update on the TSC specification. So roughly 2 years ago, I set out, not myself, but a group of people in our AASHTO NSBA collaboration group to put together a specification specifically for metalizing. And the goal was to have the owners, so all 50 states, to adopt this as their guide spec, or as their spec actually. And as how this all started is when we set out to do this, we surveyed all 50 states. We got great responses from roughly 35 of them, so which is pretty good turnout for all 50 states to get 35 responses. And we asked them stuff like, do you do metallizing? Do you do galvanizing? What do you do more of? Would you be open to a specification if we put one together? Would you adopt it yourself, or would you just use your own? So the intent was to have all 50 states just use ours. We didn't want to put out a document and have nobody use it. But we got very good feedback and input. There is currently a document that exists for metallizing. It was developed by the SSPC, AWS, and NACE. It's called CS23. I believe the new version is currently out. And it's a very good document. There's a lot of great information in there, but there were holes in there. We saw there were some recommendations that just weren't clear. So the intent of our new document was to fill in any gaps that CS23 didn't answer. So that's what our document is, a supplement to CS23. And again, we had lots of states involved. So these are just some of them that were very much involved. So I believe there were 7 or 8 states that already had a state spec. So when we surveyed all these specs, we asked them if they had one. They said yes. I called each one of them and said, hey, can I get a copy of that? I want to compare these and see where see what we can standardize and see where we have breaks. And I compiled all the results for surface prep, recommended thickness, so on and so forth. And what do you think happened? Every single one of them was different. There wasn't one that they recommended the same thing. And I even compared it to an international document. There's a really good international document that exists called ISO 2063. That's something that we use as kind of a basis to put together our document. So every state was different. So we wanted to get all these states involved and have them talk things out. And oftentimes when you get them to talk, they'll work things out together, and we can put together a standard spec that everybody uses. So that's what we did. So this is just a summary of the table of contents. So currently the document has been voted on and approved by the AASHTO collaboration. It has been voted on and approved by the SSPC. And I just got an email yesterday from Norm McDonald, who is the chair of the Steel Committee for AASHTO, and said that it's been up on the AASHTO portal for a number of months now, and he has a couple comments. So we'll resolve some of these minor comments. We believe there to be minor comments, and then it will go to vote to AASHTO at the SCOBS meeting in Spokane in June. So as soon as it's adopted by SCOBS, which we believe it will because it's already tentatively been adopted, it will become an AASHTO specification, and then all states have the right to adopt it at that point. So just a summary of the table of contents, very brief. We won't go into great detail. I believe it's roughly 30 or 35 pages or so, but a lot of information. All right, I'm going to do this quick. So the first few sections are governing specifications. We give a lot of definitions and reference standards. We talk about personnel, minimum qualifications for training for the applicator, the inspector. We give guidance on the inspectors for the owner, but clearly the owners can do whatever they want. But we do try to give at least recommendations of what we would like to see from the owner's inspectors, let alone the fabricator's inspectors. Pre-production, we talk about submittals, procedures, what you have to submit, job reference standards, give some examples of what that needs to be made up of. Equipment, so the metalizing equipment itself, and we try to emphasize dust collection. Metalizing is a very dusty process. So we want to make that clear to everybody that it's very dusty and you need to think about that before you embark in doing a metallized project. The materials, so there's roughly three different materials that you can use. 99% zinc, 85-15, which is 85% zinc, 15% aluminum, and then 99% aluminum. There's also some others that exist internationally, but they aren't very prevalent in the US, so we don't really touch on those. Surface preparation, again, this is a very important part of it. We talk about general surface preparation and also edge profile. Talk about the application, and I believe our recommendation is to use 8 mils minimum, and then there's some maximums as well, but that's generally up to the states, and we leave that up to the states. We give some recommendations of thickness, and that varies. The consensus was some people believe you can have as little as 3 to 6 mils with no top coat or with no sealer, and you still have an adequate system. It all comes down to the porosity and the permeability of the metal, of the material itself, to whether or not it's going to protect your steel or not. But the general consensus was to use 8 mils min. There's a section on sealer and top coat. Again, you don't necessarily have to have a sealer. That's just going to add cost. But some people like it and make some states feel warm and happy. But my recommendation or my perception is you don't actually need it. So one recommendation would be to add a little bit extra thickness of thermal spray metalizing and not have the sealer. That eliminates one of your procedures in one of the applications. There's a section on repairs, section on inspection and testing, and a lot of times we simply refer to CS23. We don't want to reinvent the wheel. We just say simply refer to CS23 and you're good to go. Section on handling, geometry and inaccessible areas. One of the downsides to metalizing is for very detailed parts. It can't get behind crevices, double angles, and cross frames. It's going to have a problem with that, and you might have a weak point there. So one of our recommendations, I think it's in this section, is if you're going to do metalizing, and this is in no way an endorsement of doing it, but it's a good system if done properly, is if you metalize the girder, but hot dip galvanize the cross frames. Because the cross frames are a very detailed part, and that's something where you may have problems if you actually try to metalize it. There's a section on field application, which the recommendations are pretty much the same in the shop and the field. You still have to do the same surface profile, still have the same thickness, but there are some cautions in there and some general guidance that we give. And last but not least, we have an appendix that talks about common thermal spray defects and recommended repairs. So with that, I'll ask questions. And again, the PDH code is 42172. Yeah, Dave. That's a great question, and I said that on purpose because nobody actually, I don't have an answer for you. That's where the NetPep guide would be a good reference document to go to, because I believe they give guidance in there. I can't say that with 100% certainty. Do you guys at TxDOT know if NetPep gives guidance on lifespan? No?
Well, the reason I ask is because when you look at net present value or life cycle cost of the system, it all comes down to the service line.
Yep.
Yep. Without a little more
Yeah, I agree with you. I believe the new federal highway document, the one that was published in 2015, I think it gives some guidance on lifespan, but there just hasn't been long-term studies on how long this metallized system lasts, how long this paint system lasts. There are examples out there, and I think if Bill, I don't believe Bill's in the room, he toured around Ohio, and they have some metallized bridges in Ohio that have been around for, I think, 40 years, 30 to 40 years, and they look just fine. They look in great condition. So again, I think it all depends on the details and surface prep and surface cleanliness and the environment for the application for how long they last. But no, I don't have an answer for how long they're going to last. We get that question all the time, and we can't answer it. Yep.
Can you comment on metallizing on existing bridges?
Yeah, as I just said, there are Bill McElhaney just toured around Ohio, I believe with the state bridge engineer, and they looked at a handful of metallized bridges that they've done. And they've done some 30, 40 years ago, and they looked at them all, and they're in great shape. I should have maybe had some of those pictures. That would have been good.
But I mean, now suppose you decide that as an owner, you have a bridge that was painted and you're not satisfied for whatever reason.
Oh, yeah.
And you want to switch over and
You can.
metalize it, but you're leaving metallizing outside now.
Yep. And then we had that section on field application in the specification to address just that. That's actually how it started, because people wanted to go out and metallize in the field. They wanted to change from paint or whatever to metallizing. So that's how it got its start, is to go and do it in the field, and that's where a third-party metallizer would likely do it. However, there are some owners and some fabricators who are in the room who have a metallized booth in their shop now, and they can do it in the shop. So it has application for both, but you can do it in the field, yes.
Something to watch out for if you're going to switch from a painted structure to a metallized structure is there's certain details that don't work as well for metallizing as they do for painting. So, for example, you can't go behind your coats and just daub on some metallizing.
That's right.
So if you're planning a new bridge, you're better off thinking about it from the beginning as a metallized bridge. That's where you want to go. Don't just detail it like a painted bridge and then switch over to a different corrosion protection system.
Yeah, that's definitely a concern. So that's the one downfall of metallizing is you can't get in those detailed and behind copes and stuff like that. So that's something to be aware of. Yep.
I assume it'd be okay to apply some zinc bridge coating just by hand on those spots in the kit.
Heather, I'm going to defer to you. I forget what we put actually in our... Oh, sorry. The question was, can you apply just some zinc-rich primer to locations like behind a cope or something like that? Heather?
That's pretty much your best bet.
Yeah.
I've seen metallizers be able to get in there. I've seen metallizers not be able to get in there. It depends on their equipment, on their scale, on the detail itself. So if you're planning metallizing, I really would try to get away from some of those details. But if you're going to go to your most probably corrosion susceptible areas, and that's where you're not putting your metallizing, I'm not sure you're really putting this far in.
Yeah. All right, I think we're a little bit over our time. If there's any more questions, we'll be around after our presentation.
Our next presenter is going to talk about the performance of uncoated weathering steel, Dr. Jennifer McConnell. Dr. McConnell is an associate professor at the University of Delaware in the Center for Innovative Bridge Engineering. She's a graduate of West Virginia University, where she received her PhD in civil engineering. Her research topics include bridge engineering, nonlinear behavior and stability of steel structures, aging infrastructure, design for extreme events, and computational analysis. She has participated in inspection of roughly 100 uncoated weathering structures and reviewed data from uncoated structures in 45 states. Observations from this experience is the subject of her presentation. Dr. McConnell.
Help you switch it over, or you good? Just push escape. Just click down there. Perfect.
Thank you. All right. Thanks, Jeff, and also thanks to Jeff for setting up this talk beautifully. He gave a nice introduction on the concept of weathering steel. He made the comment, when designed and detailed correctly, so I'm going to elaborate a little bit on exactly what that means. And if you've seen me talk on this topic before, it's the same basic talks about the same basic research project. It does have a little bit different flavor, as I've given this research talk a few different times. One of the things that I'm starting to see is questions about how we inspect weathering steel, so I've added some comments about that to switch this up a little bit. So the starting point for this research, the starting point for most owners or designers who are thinking about using weathering steel, is usually this 1989 technical advisory on the use of weathering steel published by the Federal Highway Administration. It gives detailing and maintenance guidance. It also gives general information on environments where it's phrased uncoated weathering steel should be used with caution. And all of the things listed there are very logical. They are appropriate guidelines. The limitation, though, is a lot of the guidelines are very qualitative. It says marine coastal areas. As Jeff mentioned, he showed a nice photograph of the beach. That's obviously marine. What if I'm a mile away from the beach? What if I'm anywhere in the state of Florida? So what exactly does marine mean? And that was part of the scope of our research, was to find some quantified metrics that we could use to supplement this guidance from a few decades ago. So what I'm going to talk about today is really a combination of research that was done as part of the Long-Term Bridge Performance Program. That was a nationwide study, very detailed, and then also to supplement that with some of my observations from doing inspections on a West Virginia DOT project that, as was mentioned, was about 100 weathering steel structures. This involved a few different assessment methods. We surveyed owners. We did a pretty rigorous analysis of data in the NBI, just to give a high-level overview of performance. And we relied on visual inspections from the owner's inspectors, as well as doing our own independent inspections. And the results from this we looked at in terms of macro environment, which Jeff talked about. Does that mean marine, industrial, rural? And also in terms of micro environment, which means obviously the climate in Texas is different from the climate in Delaware, which is different from the climate in Buffalo. But microenvironment refers to the fact that even within Delaware or Buffalo or Texas, there are different humidities, there are different crossing types. Some bridges might cross a heavily salted I-95. Some bridges might cross a road that never gets salted. And there's a lot of differences that come about based on those microenvironments. And then to also talk about results in terms of maintenance and detailing. So one of the first ways that we looked at micro environment performance was to survey the owners of all 50 states, Washington, D.C., and Puerto Rico. And this was an open-ended question. What do you think of the performance of weathering steel within your jurisdiction? And then classified their responses in really 3 distinct categories that emerged based on this open-ended question. So all but 2 owners gave a positive response. So positive meaning it performs well. We called that an entirely positive. We're saying it's our preferred material and no other qualification to that statement. We said that was an entirely positive response. Some other owners might say something like, well, it performs well, but we see a problem when it's used over a heavily salted roadway. So we called that a mostly positive response, for example. And then only 2 agencies gave us a negative response. And I think it's very important to note that neither of those 2 agencies have constructed any weathering steel bridges since that 1989 guideline was published. So they have no newer bridges made of weathering steel, and they have no bridges that were necessarily designed or detailed according to our modern guidance. So I'll let it stand at that. You can make your own conclusion based on that. So another way to look at microenvironment is to look at this more qualitatively based on climate categories. This comes from the International Code Council's way of classifying climate, where temperature is a numerical scale, 1, 2, 3, 4, 5, 6, 7, 8. The higher the temperature, the lower the number. So Florida's a 2, South Carolina's a 3, Virginia's a 4, so on. And then more humid areas in the eastern 2/3 of the country are category A for humid. The western half or western third of the United States is dry or category B. So to look at the bridges within each of those climate categories and look at how they perform. And so what we see here is looking at the NBI ratings of bridges in those climate categories and what the distribution of those NBI ratings are. So for example, what percentage of the bridges have a rating of 8 or 9 would be green, ratings of 6 or 7 are blue. We see, first of all, there's not that many that are low ratings. And we also see that there's no clear trend here. So as a function of macro environment, there's really not any clear trend that really emerges here. Another way of looking at how weathering steel performs as a function of microenvironment is to compare it to painted steel structures. So again, this is high-level aggregate data from the NBI plotting the superstructure condition rating versus age, because we expect the rating is going to go down with age. We see there's a lot of scatter here, and every bridge that is weathering steel is a data point. Every bridge that is painted steel is a data point, and so you can't really see anything when you just look at this mess of 1,000 data points. But if you apply a trend line to this, the solid lines are the trend lines for weathering steel in 2 agencies, and the dashed lines are the same agency's painted steel. So you see that weathering steel generally is performing better. As we get to older bridges, the trends change a little bit, but again, that's before the modern guidance. The same could be said for paint, though. Those are older paint systems. So for newer bridges, it does seem like weathering steel is performing better than paint based on this data. As we move into looking at the microenvironment, the approach here was what we called a cluster approach, where we picked 4 geographic regions and we established bridge clusters, which were really groups of about 20 bridges within a 50-mile radius of one another. And these were selected looking at outliers in performance. So for example, this cluster near Buffalo, New York is not just good performing weathering steel, but it's good performing weathering steel in an area where there's 90 inches of snow a year, there's many major interstates, heavily salted, high ADTs, and it's still performing well. So these were things we wanted to look into more carefully. And then there's also places where the weathering steel was performing not as well as the owner expected, and there really wasn't any obvious reason why that would be. So we were really focused on trying to understand outliers in performance, and there was a very robust statistical analysis used to select these. And so here we're looking at very detailed inspections of each of the bridges within this cluster. So for example, just looking at superstructure condition from the NBI for thousands of bridges, now we're looking at very detailed evaluations for a smaller number of bridges. So really 2 opposite ends of the spectrum here. So visual assessment of weathering steel. At the time we did this research, most of the owners had already adopted the guidelines in the AASHTO 2013 Manual for Bridge Element Inspection, which has a condition state rating scale of 1 to 4, 1 being the best, 4 being the worst, which is then applied to every element in the bridge, and then not only that, but also the amount of that material in each condition state. So for example, I could have 10 linear feet of my girder in condition state 2 and 100 of it in 3 and 50 of it in 1, or any distribution like that. And so for weathering steel, these general descriptors get translated into condition state 1 says no defects, condition state 2 says pitting, condition state 3 says section loss, but I haven't lost any capacity, and condition state 4 is that I have section loss to the extent that I have reduced operational capacity. So this distinguishing between condition state 1, no defects, and condition state 2, some corrosion, is really critical to moving forward with the research and figuring out the performance of weathering steel. So we want to look at that a little bit. So condition state 2, pitting. Here's a couple examples of bridges that very neatly fall into that category. However, this bridge on the top left, you can probably see, depending on the lighting, this is crossing a navigable waterway. Not only that, it's crossing a navigable waterway less than 1/10 of a mile from the Gulf Coast in one of the most humid locations of any of the bridges we looked at, with the highest atmospheric chloride concentrations of any of the bridges we looked at. And so there was a lot of debate during the research whether this level of corrosion, the bridge is also close to 40 years old, is really a problem, or is weathering steel really doing a good job here? For example, would paint be performing better, or any of the other systems that are commonly used? So yes, this is pitting, but not necessarily an indication that weathering steel was the wrong choice here. This example on the right I chose because, again, this is obviously pitting, but when you're looking at this photo taken from the abutment, the weathering steel, you can't see a problem here. So this I just want to highlight from an inspection standpoint. You really do need to get a closer view than just standing at the abutment and looking from there. So those are examples that fall very neatly into condition state 2. There's a lot of examples where we're looking at steel and it doesn't neatly fall into any of those 4 categories. And so inspectors really struggle with what they should do in this situation. So this photograph, there's no pitting, there's no section loss, but it's also questionable whether this is really no defect either. So a way that we came up to deal with this issue in a more quantitative way was to use tape samples, which is probably the most low-tech testing any of us have ever done. It involves simply taking a piece of packing tape like you would buy at Home Depot, sticking it onto the surface of the steel, ripping it off, and sticking it on a sheet of white paper. From there it gets slightly more high-tech that we use, scan that in and use image recognition algorithms to analyze the size and the distribution of those particles that stuck to the tape. But so it's a very simple technique. The benefit of that is we see a clear gradient in what these tape samples look like for bridges that have pitting and bridges that had no defects. So the ones in green are the average average percent of these large particles for bridges that were in condition state 1. And then the ones in orange are the same data for bridges that were in condition state 2 with pitting. So this allows us, for these intermediate cases where it's not pitting, but it's also not exactly no defect either, to have some quantitative measure for classifying the performance. Another thing we need to understand about this data, though, is that these samples come from several different locations on the girder. So those are the circles, are the cross sections where the data is coming from. It's also coming from different girders, different longitudinal positions along the length of the girder. And there's a gradient in what those tape samples look like at different locations. So it's probably no surprise, for example, that up here at the top of the web, we have less corrosion than at the bottom. So in a good performing bridge, you might get a range of these tape samples where you have just a few tiny dots. This might not even be corrosion particles. It's possible this is just dust. Mostly it's going to look like this as the average. And maybe on the higher end you see some where about 8% of the space is occupied with these larger particles. For an inferior performing bridge, you have a case that looks as bad as this in some cases. So it's pretty clear when you look at it from this perspective which bridges are performing well and which ones have some active corrosion. If you were thinking of applying this, we looked at many locations along the bridge. The worst case scenario are the top surfaces of the bottom flange, and specifically of the possible girders. If this is a highway overpass and traffic is traveling from left to right, in this first interior bay is where the largest corrosion particles were typically found. If you had a waterway crossing, there's more uniform corrosion. That's still a good place to sample. So some concluding comments about visual assessment. It's highly dependent on what should good performing uncoated weathering steel look like. And the qualitative statement is it should have a tightly adherent patina and it should have a fine-grained patina. So those are subjective terms. So the tape sample gives us a quantitative way to apply some consistency to exactly what that means in the inspection process. It's also worth noting there's been some work done in Japan where they have also looked at these particle sizes and correlated that to corrosion rates. So, there's a real opportunity there, I think, to make this a more engineered process. So the results of those visual assessments were used to classify all of the bridges we looked at into two categories, that there was active corrosion or there was not active corrosion. And then based on that, we plotted those bridges as a function of different parameters. So for example, for the bridges along the Gulf Coast, we have humidity on one axis and distance to the coast on one axis, on the other axis. So there are two bridges in the Gulf Coast that we classified as having active corrosion, and we see what they have in common is they both have a very small distance to the coast. It's less than 1/10 of a mile. Humidity is not necessarily as clear, though. We see bridges that are in more humid locations that were fine. So what this is showing is that it's not just these two variables. There's a third variable, which is chloride concentration, that explains this difference. So if you could easily see a 3D graph of this and have chloride on a third axis and plot these orange data points where there's corrosion are in a different three-dimensional space with higher chloride concentrations than the other bridges that do not have corrosion. So it's a combination of distance to the coast, humidity, and chloride that we've quantified. On the right is the same type of data, but for bridges over roadways treated with de-icing agents. And here we see the main parameters were vertical underclearance and the ADT of the highway underneath the bridge. So this is really a direct measure of how much chloride is getting onto the bridge from the salt spray. Again, there's some trends here, but there's also outliers and not everything's grouping together. And that has to do with how much snowfall is at the location, how much atmospheric chloride is in the air at the location. So again, if we could have a four-dimensional graph, those orange data points and the green data points separate themselves into different spaces. So the conclusions of that for the coastal clusters are we were able to identify what we called a consistently inferior environment. So for a specific combination of distance to the coast, humidity, atmospheric salts, and crossing a waterway, the bridges in our study that had those criteria consistently had active corrosion. And then in contrast to that, we also identified several combinations of environments where any combination of those, all of the bridges had good performance. And there's a reference there if you want to read all of the details about that. We also made similar conclusions based on the clusters in the de-icing, what we call the de-icing clusters in Maryland and New York, where again, the consistently inferior environments were highway crossings with a vertical underclearance of 5 meters or less. And then also having certain combinations of a really high ADT or a more modest ADT but a lot of snow, or a smaller level of snow but a lot of atmospheric chloride concentration. So those were things that emerged as observations based on, here I need to qualify, this is a 40 out of about 4,000 bridges that could be in this category. So this is a more limited analysis. But
What is ADT? What does ADT stand for?
the average daily traffic of the ADT is the average daily traffic on the highway that the bridge is crossing, so not on the bridge itself. The consistently satisfactory environments, there's also a few identified there. So the next thing we looked at was, okay, this is trends that emerge, but how confident can we be on these conclusions? So we go back to the NBI, and the first thing we need to decide is what exactly is the definition of coastal? So we could look at this a couple different ways. Does coastal mean it's in a state that borders the Gulf Coast? That's pretty extreme. Another one is if it's within 50 miles of the coast. And look at the average NBI ratings of the bridges that fall into those consistently satisfactory or consistently inferior, or what else is left. So if we look at the coastal, it looks like those conclusions are pretty good. The consistently satisfactory bridges have a higher average NBI rating than the ones that were in neither category, which has a higher rating than the ones that were in the inferior category. So that's some support for those findings. The de-icing, it was no surprise that there's not as good of a good correlation here, again, because of the volume of data we looked at compared to the samples of bridges that actually exist. But we did find that the average rating of the bridges in that consistently inferior environment was statistically significantly lower than the rest of the bridges in that region. And then a final way of looking at this, just for the coastal correlations, because we did have pretty good confidence that we looked at a good sample size here, and we went back and found outliers in the NBI and then requested from the states their inspection report. And so for that consistently inferior environment, there were no other bridges in the entire US that met that category that weren't a part of our study. So what that tells us is that that is a very severe environment that we identified. For the consistently satisfactory environments, we looked at 18 other bridges, and all of those were performing well. So when it comes to the coastal clusters, we feel like we've looked at a large amount, a large percentage of the bridges in that area, and we have relatively high confidence that those environments are good for giving owners some quantitative guidance about what a coastal environment is. For the de-icing clusters, we've only looked at about 1% of the bridges within that environment, so there's low confidence to really apply those numbers. And so our next step there is that we've recommended future research to further look into that. A couple disclaimers on this. It's based on a possibly arbitrary threshold of condition state 2, meaning that we don't know what that means in terms of corrosion rate. So to quantify this in terms of corrosion rate would be a much more thoughtful and an engineered process that we simply don't have the data to evaluate right now. This also assumes all conclusions are based on bridges that were detailed according to that 1989 Federal Highway Technical Advisory. So everything in there we're recommending to continue to be implemented. All right, very quickly, a couple comments and observations based on maintenance and detailing. By far, both on field inspections and the long-term bridge performance program data that we looked at, the biggest contributor to corrosion of weathering steel has nothing to do with humidity or de-icing agents directly. It has to do with a leaking joint. This is the bottom flange peeling off at an abutment underneath a leaking joint. This is also obviously not a problem that's limited to weathering steel. All of our materials are going to suffer when they're under a constant wet environment. For the bridges that we looked at as part of the cluster study, 70 bridges, 23 of them had corrosion that was worse at the joint, and it's not just limited at the joint. Once there is a problem at the joint, the water from there travels longitudinally along the rest of the bridge. So 23 out of 70 bridges had a problem at the joint, despite having the end of the girder being painted, according to that 1989 technical advisory. So that's something we should do. We should paint the end, but we shouldn't think we've painted the end and therefore everything's fine. It's very critical that we need to maintain these joints. It's a very cheap solution to preventing corrosion. Another observation about maintenance, we've seen cases where vegetation is growing around the structure. It makes a very humid environment. This is a hole through the web because of this, or at least exacerbated by it. With respect to detailing, the simplest way to think about this is all structures are better if they have a roof. So for girder bridges, that means this is a pretty narrow overhang. So this bottom flange is just rain collects here. Not only that, capillary action pulls that water up the web, and the lower part of the web is starting to corrode as well. So as wide as we can make the overhang within reason is better. This is an even worse roof. This is a very leaky roof. There's a lot of examples in rural areas where they've used timber decks or these filled concrete decks with weathering steel bridges. Water gets through the deck and then can evaporate, and there's always corrosion problems here. And so for girder bridges, that's pretty simple to detail these. If we're using weathering steel in arches or frames, we really need to think about where the water is going to go. It's going to run down this and collect at the bearing, and then we see puddles full of mud. There's visible section loss here. So just to be thoughtful about what the path for the water is going to be when we detail these. So some conclusions. First of all, I want to point out these were conclusions based on weathering steel because that was the scope of these studies. None of those findings are guaranteed to be specific to weathering steel, though. For example, that environment, it's an extreme environment. There's no guarantee that paint is going to perform well. They might be environments where you look at one of those higher cost options that were mentioned earlier of metalizing or galvanizing. But this doesn't mean weathering steel doesn't perform well, so I should use paint instead. We also found the performance is more dependent on the microenvironment than the macro environment. And this macro environment for coastal, we feel that we've quantified with a reasonable level of confidence. Also some comments about detailing and maintenance, particularly with joints. It's, like I said, a very cheap solution to an expensive problem to maintain the joints. So with that, if we have time, I'll take a question or two.
Well, we can take some questions now, and if we can't get through them all, Jennifer will be available following the presentation. Go ahead.
I remember a building where I went to college, which was it was a new building. It was back in the 70s, and it was built with weathering steel. The steel had been developed, had been used before in Pittsburgh, which is an industrial environment, and this was in a sort of rural setting, high rainfall. What happened is the patina would get washed off with the rain, and it was streaking the glass on the windows, it was staining the walkways. No chloride, okay? It was just wet weather. So I agree with your point that you've got to be careful in wet, high rainfall areas.
Yes?
Are you doing research on corrosion rates of weathering steel? Because again, when you look at 100 or 150 year service life, and you're making a choice between weathering steel and painted or metalized, that gets the matter.
Yeah, the question was if we're looking at corrosion rates. So what I showed here was the results of phases 1 and 2 of a long-term bridge performance study that was intended to, and is intended, I still believe, to have a third phase. And that's maybe something we could look at then. I totally agree with you that is what we need to know. There's some literature, if you want to talk to me later, from Europe where they have looked at corrosion rates. I'm not sure how applicable it is because their climate is slightly different from ours, but I think it's better guidance than nothing. So.
Is it more than the literature from Spain?
It's the one from Spain, Morcillo. Yeah. Yes.
In some areas in Canada, for some reason, the EOPs will use weathering steel and paint, thinking that they will reduce their maintenance in common.
Yeah, so the question was if I could comment on the practice that some Canadian agencies use to paint weathering steel, kind of like belt and suspenders, I think is what some people call it. I have mixed feelings about it. I think that the paint is obviously should be protecting it. The problem with the paint, as with any painted system, if once the paint has some flaw in it, that's where all the corrosion is going to concentrate. The water will start to seep through the paint at that point. So I can't say that it's good or bad, but that's something I think I would try to be more thoughtful about whether I really need it or not. Use maybe some of this as a guidance for that. Yes.
Have you ever thought of these corroding bridges in terms of anodic and cathodic areas?
Mm-hmm.
Because what I find dealing with repairing other kinds of corroded structures, we found is that you have anodes forming
Mm-hmm.
a lot of corrosion. So what it is, the structure is like a big battery.
Right.
And there's current flowing. Has anybody thought of a way of ways of arresting that electron interchange? Stopping it
Yeah,
from forming?
right. So there's cathodic protection systems that a few owners have applied to apply a current
Yeah,
to.
usually that's for submerged applications, okay? But exposed girder
Mm-hmm.
would be, but has anybody thought of?
Yeah, I think there's not a big current differential on the weathering steel. I think it's pretty uniform throughout.
Well, usually what you'll find is if it's in contact, parts of the girder are in contact with dry concrete, parts of the girder are in contact with moist concrete, that you will
Yeah.
establish that current.
Right. Yeah. Maybe that's phase 4 of the study. Yeah.
Defer the rest of the questions to later.
Okay. Thank you.
Our final speaker for this workshop is Ronnie Medlock. He'll talk about fabrication cost comparisons for durability solutions. Ronnie is the Vice President of Technical Services at High Steel, has 25 years of experience in bridge design, fabrication, and construction. He's responsible for engineering and quality control at High Steel, and he also oversees operations that include detailing for erection and design of erection procedures. Ronnie is active in AREMA, AWS, TRB, and NSBA, where he chairs the technical subcommittee of the NSBA Executive Council. Thank you, Ronnie.
Thanks very much, Gary. Brad, don't worry, someone pulled an old bio, so I'm not doing engineering anymore, and Brad's here, so it's not some news you don't know. And also, you'll see my name wasn't in the program. Deb couldn't make it, so I'm filling in for her.
This one is yours?
Yeah.
Okay, here you go.
Okay, thank you. Thank you, John. Okay. Yeah, this is a presentation that I gave earlier this year. There was a workshop at TRB about durability solutions, and I was asked to provide the fabricator perspective on durability solutions. So some of you may have seen this before. As I said, I'm filling in for Deb, and so I had this ready, and I hope you'll find it interesting. This presentation will focus on our perspective as a fabricator, what we care about, what we execute. So not recommendations on durability solutions like Jeff was providing, but more how we execute them. So in terms of our perspectives, what we care about, first of all, you can sum up what we care about in terms of quality, schedule, and cost. Probably the thing we care about the most is quality. Certainly everything that we execute has to be done to the spec. As a fabricator, we're committed to performing to the specification. And further, it's important to us to deliver a job that we're proud of and that we've done a good job. So when we're looking at our perspectives on what solution is called for, we're thinking about, well, how do we execute that to achieve quality. The next thing is schedule. When we take a job, we make a commitment to deliver on a schedule. Of course, to the contractor, that's crucially important. So when we look at the coating or the durability solution, the coating, etc., we're thinking, all right, how long will this take? Make sure that that kind of time is in our plan and we can execute. So one of the things that might be important to you is understanding, well, how long do these solutions take, especially if you're on a time crunch. It may be that the time it will take to do the solution won't supply your schedule. And as you'll see from my presentation, there are some methods that take a lot more time than others. So that's important to understand. And of course, the other thing is cost. And on the one hand, we don't care about cost. And what do I mean by that? As a Gary's, shaking his head, what am I talking about? Well, what I mean is this. When we get the plans, we read the specs, what is called for, we put it in the job. If it's weathering, we don't add anything for cleaning, painting. If it's clean and paint, well, we put it in there. And then when we go and do the job, we execute it. So from that perspective, it doesn't really matter. On the other hand, what does matter is if we go to execute the solution and then there's unknowns or things that come up that we didn't expect, and that maybe slows us down and impacts our schedule, or, oh, there was something in here that this is what I really meant, we have to do some extra effort, and that starts adding cost. Those kind of things we certainly care about. And also from a perspective as an industry, we hope to see the most cost-effective solutions out there because we are competing with other materials, and we want steel to be the best solution from a variety of standpoints, including cost. So then in terms of what are the things that impact those values, it comes down to what we do. And as you'll see through the solutions that I talk about, that the basic steps involve the cleaning, the masking, then that application of the coating, if there's a coating, handling and moving. Often people who aren't aware of what we do forget about that. But that has a significant impact in both time and cost. When we cost out a job, we know, well, it's going to take so many girder moves and that costs us this much, and we put it in there. So there's a cost and a time impact from that. And then waiting. Jeff pointed out that in some of these solutions you have to wait. That may not necessarily have that cost impact, but certainly can have a schedule impact. So those are the various things that are involved, and as you look at the comparisons, that'll come out. So I'm going to do some cost comparisons. I can't tell you what our cost is. It wouldn't be legal, and besides, I don't want to reveal that. But what I can tell you is a rough idea of percent increase. Okay? So as I look through this, I'll say, oh, you might add another 25% if you do that. You might add a 50% if you do that, that sort of thing. So to arrive at that, we use this bridge as a basis of comparison. Your intuition will tell you, well, that percent increase is going to vary with the bridge, right? Because if you're doing something that's complicated, maybe the coating won't impact as much, or maybe it would, certainly. But for the basis of comparison, we just took a typical grade separation bridge like this one. I said, all right, if this is the base cost, what is the percent increase? And I don't give you the base. I just tell you a percent increase, okay? So durability strategies, the first is weathering. Of course, Jennifer gave you a very thorough explanation about weathering steel. We like weathering steel a lot. It's very easy to work with. I'll comment that when I was with Texas DOT, we did a study of the weathering steel bridges. We saw the staining that we sometimes got, and we said, is that weathering really working? We still see rust, so we must not be getting the patina. So we looked at 30 bridges, and what we found was interesting. I think the bridges at that time, the oldest were about 20 years old. And of the 30 we looked at, only one had a patina yet. They were corroding so slowly, and a lot of them didn't have a lot of moisture available to them, that we weren't getting the patina. The one where we saw a true patina was a coastal bridge. Okay, we looked at bridges, including in Houston, where they get 60 inches of rain, and still taking a long time. In fact, some of those bridges had mill scale yet on them. So at least in Texas, we found that we were getting really good performance. So painted, the percent increase for painted, what would you think? I'm not going to ask you to raise your hand or answer, but I'll get you thinking about it. What do you think it would cost for 3-coat paint? On that bridge, 24%. So if you decide that bridge I showed you was weathering and you decide, oh, I'm going to paint it instead, you'll add 24% of cost. That cost is involved in cleaning. You're going to blast clean, moving, because you're going to move the girders from where you were blasting them to where you're painting them. And then if you think about a 3-coat system, a lot of handling and moving, right? And then adding the paint. So add about 24% if you paint. Galvanize, 41%. Where does the cost come from when you galvanize? Well, galvanize, no fabricator, at least that I'm aware of, has their own galvanizing operation. So that will be subbed out somewhere else. So we're going to ship the girders over there. The first person who's going to do the galvanizing will go through those operations. Jeff described them to you. So in terms of our cost, well, that's what they tell us that we're going to get and put it in the job at about 41%. Metalized, similar, very similar to galvanized. Of course, very different operation. As Jeff mentioned, some folks have that in-house. Our company has metalizing in-house. We're cleaning, but a big difference is that the expectation on a metalized job is that it has to be hand blasted to give you a deeper anchor pattern. Fabricators, we all have wheel abraders that automate that cleaning process for paint, but those wheel abraders will not give you the anchor pattern you need for metalizing, so you have to go back and hand blast it. So you can imagine, it takes a lot of time. And then the application of the coating takes quite a bit of time as well. Metalizing will build at about 2 to 3 mils per pass. And typically you're seeing specs that are around 10 or 12 or maybe 15 mils. So you think about that, how many times do you have to stand there and pass? Of course, metalizing is not like paint. It doesn't have to dry. It only has to solidify. So you can build it fairly quickly. Still takes time. And of course, you're buying that zinc wire as well. So that's about where your costs come from. And then A1010, newer solution, 130%. A1010 is a newer steel, high chrome. I think it's like 11 or 12% chrome. So you're paying for the chrome. So pretty expensive material there. So taking a closer look at each one, some nuances on weathering. Sometimes we do end paint for weathering, especially in the East Coast. Popular under the joints to do that. Doing that will add 8%. What about end and fascia paint? Sometimes we do solutions where we'll just paint the fascia, 10. If I look at those end painted bridges, I really don't think they look good personally. That end paint always jumps out. You may think about that. It's not going to add that much more to do the whole fascia, because if you think about how we're going to go about doing that painting of that end, we're still going to have a similar operation. We're going to clean the girder, we're going to set it up for painting, we're going to go over and paint. It's not as much paint, but it's still quite a bit. So just going a little further and doing the fascia won't cost you that much more. And then painting and weathering, that came up in Jennifer's presentation, 27. That's not really a painted, a weathering solution. It's more of a painted, and I'll talk about that again. But yeah, folks do sometimes like that belt and suspenders approach. Yes?
Is the base cost of weathering including the blasting that Jeff mentioned before?
Let's see. That's a good question. Let me think. The question is, does my base cost of weathering include the blasting? I'm not certain. Sorry. I'll be sure, and I'm not certain about that. I would assume so, but I'm not sure. So now looking at the painting strategies, I already told you if you paint, you'll add 24%, or if you do weathering, you'll add 27. Similar between IOZ and OZ. And by the way, these symbols I've got here, WP, WP. I'm putting that up there so we can do a broad comparison later, okay? And then the two-coat, 19. Jeff was telling you about that polyaspartic system. That's a system that we like. And it makes sense that if we're only doing 2 additional instead of 3, it won't be as much of a premium, okay? It's important to go into a little more detail about inorganic versus organic. As Jeff mentioned, curing time can be an issue on inorganic zinc. Inorganic has to have moisture to cure. So you need to have a humid environment. You have to check on the cure. There's testing you do to make sure that you have cure when you're doing inorganic. Some owners will put time in there, like he said, one that has 3 months. They want to be absolutely sure that inorganic is cured. So think about the schedule impact. If a project has 3-coat paint and you have months that you have to wait, you'll go through that whole operation. You'll take that outside, right? There's no way you leave it in your paint bay because it would plug up your paint bay. You leave it outside for 3 months, bring it back in. So doing that obviously has bigger cost impacts as well as schedule. But even if you're not doing the months, you still have to wait for that cure. So when we look at a schedule, especially on a big job, we may see something that says, oh, you know what? That job calls for inorganic zinc on that schedule. You can't get there because the hours are the hours of what they are. So it may be that you would put something out there and you say, you know what, that can't be executed. You may not get bids. So in terms of the organic, that's something that's very important to think about. And then that also impacts capacity. If a girder takes longer to go through our operation to accommodate it, then we only have so much capacity. So we're also looking at, hey, can we execute that job based on our capacity, which is a factor of how long it will take to paint, including that wait time, okay? And then a little more about that polyaspartic. Jeff was mentioning it. We've done 2 jobs. Here's a picture where we did some tests. The coating has been around for a while. It's used in field application. It wasn't popular with fabricators before because it would dry too fast. And if a paint dries too fast, then we have quality problems. We'll get overspray and we can't build it up effectively. So we had looked at it and others had looked at it and said, no, you know, that's just not doable. But we're looking at this EnviroElastic 980, which is a Sherwin-Williams product. And they dialed it back a little bit. And so we said, well, sounds good, but you know, is it really going to work? We did some tests, and we really liked it. This is Pat, who runs our paint bay, and these were his comments. You can read them. We've since done 2 jobs with the polyaspartic. You know, if you think about the 3-coat versus the 2, as Jeff mentioned, you add the epoxy, it gives you a barrier, but it helps you bind the urethane. The polyaspartic accomplishes what both of those coatings do. So yeah, I think if you're into painting, you may want to take a good look at the polyaspartic for the speed. It is a NEPCOAT approved paint. If you look at the NEPCOAT menu that has ABC, C is field. So they say approved for field, but if you look at it, I think you'll find it's also effective in the shop. So we like it for the speed and the capacity that it would provide. I think it's worth looking at. So a little further about galvanizing. I told you add 41%. If you do fascia paint, 54. So every now and then we'll get a job that gets galvanized and paint. Well, that's got to come back to the shop, go through the cleaning, go through the application. So you'll add quite a bit more to paint that. Metalizing strategies. I told you that we add 42%. That does not include sealing, okay? Because what we see is typically not sealed. But if you seal, add another 7. Once again, you're adding a coating application, okay? Metalizing sealed and metallized frames, 54%. So my assumption when I showed you that number or I show you 42%, that assumes that a bridge has galvanized cross frames, which is the most common solution when you have a metallized bridge. But if you say you want to metalize the cross frames, it's going to be pricier because you have to pay for these things that are down here in the bucket. And I'll come back to that in just a little bit. What is that in the bucket? So a little bit more about metalizing. Growing in favor. We're starting to see that more. We do that in-house. I think maybe 7 or 8 different owners we've done metalizing jobs for. Capacity is an issue. It's a slow process. So, fabricators who are going to do that, if you're looking at a metalized job, you need to think about, well, when do I want that executed? Once again, the bigger the job, the more you may have to think about the time it's going to take to do that metalizing, which relates as well to the schedule. This standard is the same thing that Jeff mentioned. That standard is on the SCOBS ballot for June, as he said. So we anticipate that it will be approved. It is a struggle to deal with 7 or 8 different specifications. The pull-off values vary. When you do metalizing, you have to put these tabs on and then pull them off to make sure that you have adhesion. So there's different requirements and those pull-off values. There's different requirements in how often you should do those. There are different requirements for anchor pattern. So it would certainly make sense to go to a standard. Jeff led a team with a very broad group to really come up with the best consensus standard. So I'm certain in saying that standard is the best metalizing spec available. So if you're going to metalize, I highly encourage you to simply specify that document. Okay. Approvals have been an issue on some metalizing jobs because we have to submit procedures and then they need to get approved, and that can take time. Galvanizing is superior to metalizing for cross frames. This is our opinion. I think it's a pretty strong consensus opinion. Not everyone agrees. I'll go back to those tubes I was showing you. This was a job we did about 5 or 6 years ago, and the owner called for metalizing the cross frames. When we see jobs like that, we will send in an RFI and say we recommend galvanizing them. Galvanizing is really good for getting into nooks and crannies and getting a very complete coating. To metalize effectively, you need to clean the steel and then apply the spray. The spray comes out of a gun in a wide pattern. You want to hit the material squarely on. So you take a look at this cross frame and you think about, well, that's a lot of different moves trying to make sure I get every nook and cranny, and how do you get behind? And in this particular case, because this cross frame had double back angles, we had to do one side and then do the back side of the other angles, which you see here. Okay. Is it point? Middle. Okay. Okay, thank you, Jeff. So we've done the back side of these angles, the front side of that whole frame, then assembled it, and then put these tubes into these, I guess it was hose, into these slots to protect the metalizing that was in there, because then we need to go back out and complete the cleaning and complete the metalizing. So lots of handling. We executed it, and I feel comfortable that we accomplished the job to the spec, but I'm not comfortable in saying that you'll get near as good a job as you would just dipping those frames. And it is, I would say, a very strong consensus in the community that it's a better way to go. Not everyone agrees. The project manager on this job said no, metalizing is better. He wants it, and we bid it, so that's fine. We did it. But I would not agree with that recommendation. So, and similarly on this job, same kind of thing. This is a cable stay bridge that we did for New York, just wrapping up. The girders were metalized, and these anchor assemblies were galvanized. So once again, it's a better solution. If you were to try to metalize these components, trying to hit all of these surfaces squarely, and then getting behind corners, etc., inside that pipe, very challenging. I don't know effectively how you could really metalize inside of that pipe. But galvanizing is very simple. Why not just galvanize the whole job? Well, galvanizing is limited by the size of tanks that are available. So, we do a fair number of small bridges that are galvanized, and if they're small, that's easy. If you get to a certain size, as Jeff said, you can double dip. That starts to break down the bigger and bigger you go. So on a typical bridge, which has deep girders, that if you're going to look at metalizing and galvanizing, if you have these smaller components, cross frames, galvanize them, but metalize the bigger girders. Okay. I have a question about the anchor profile. This is just my own personal question. With that metalizing requires the hand blast for the anchor pattern. I wonder how well it would work on just a blasted girder. I think it would be nice to study and see if it would perform, and then maybe bring that down. But that's just more of an R&D kind of question. So I told you that girder, that project, metalizing increased it, on that first bridge by 42%. This bridge is much more complicated, a lot more work involved. The increase for metalize and galvanize was 18 on that. So that kind of gives you a bookend. If you have a highly complicated job, that increase for the coating won't be quite as much as it was for just a typical overpass. Once again, the A1010, 130%. Not a lot of additional detail about that. Oh well, I will add one thing. The assumption with the A1010 is galvanized frames at 130. Okay, we did one bridge that had metalized girders, galvanized frames. If you were to use A1010 on the frames, that would shoot up quite a bit more. So here's the overall big picture of the various solutions compared graphically. If you're in that weathering range, end paint, fascia, painting, you're starting to add around 25%. There's one here I hadn't discussed, prime only. Of course, some places, including Texas, you don't do the 3 coats in the shop. So that changes that dynamic a lot, especially for that inorganic question. If you're inorganic but then doing the intermediate, the field coat in the shop, then you have plenty of waiting time because it's going to come out of the shop, it's going to go to the field. And that's just one additional coat. Galvanizing, metalizing in this range, depending on the solution you choose, up to A1010. So in summary, certainly weathering steel is the most cost-effective, especially in terms of upfront cost. If you are going to paint, I would recommend using the inorganic zinc, especially for schedule and capacity. And then take a look at that polyaspartic top coat. Remember that polyaspartic will go on an inorganics 2-coat system. If you're galvanizing, only galvanize smaller bridges and smaller components. Really big things you can't get in the tank, or you can't do that effectively. And if you are metalizing, then galvanize across frames and smaller components. Just one last note. This happens to be a metalized bridge that we did in New York, the Lake Champlain. I think it's very nice looking. And sometimes there's questions, but well, how well does metalizing look? When you're up close to it, it has a splotchy look to it. But when you stand back, I think it looks pretty nice. All right, any questions? Yes, back.
Yeah, the last part of your relative cost table is what percentage of your cost for that span bridge is the raw material itself, plate steel?
Yeah, I don't want to reveal that. I just want to give you a. Yeah, you're just going to have to. You could get steel prices if you want to. I simply want to tell you, if you take a typical bridge and you do these things, that's going to be the increase.
If you're looking at life cycle, again, if you're looking at present value or life cycle cost, the corrosion loss rate that factors into the material cost, which I assume it doesn't cost any more well than a 3/4 inch plate than a 1/2 inch plate, but if you're putting fillet on time, but the loss rate is what factors into the NPV.
Yeah, and so would that choice between the weathering steel plate and the price of the material factor into your model? I suppose it might. So what I would do is go back and look at, well, what would that plate be? And if you had a discrete job, you could probably get cost information. But from a big picture, I don't want to tell you. I want you to know that generally, here's the direction. Here's here's the relative cost of the solutions. You had a question?
Yeah, it's just, I'm still with the blasting cost in my head, so I want to rephrase the question.
Yeah.
Is the blasting of weathering steel a market requirement or a best practice for a nice patina formation?
I would say it's both. Some specifications require blasting, and I think that that model is with blasting. And one blast is not typically very expensive. Fabricators all have wheel abraders. It's a mechanized process. We put it through. So I think my base cost included one cleaning, but I'm not sure. All right, thank you. Oh. And finally, our code 42172. All right.